In this lesson, we are going to look how to solve counting problems that involve permutations and combinations. So now we're going to have to sort out where order is important and where it's not, and know which formula needs to be used. So let's think about this first. What do you notice in the two scenarios below? There are 5 swimmers in the first heat of a race: Abby, Bree, Callie, Deanna, and Emily. How many ways can the 5 swimmers finish first, second, and third? And how many ways can the 5 swimmers qualify for the final race if the top 3 finishers qualify? So what's the difference there, and what can you tell me about the two different questions? Hopefully you've noticed that order matters in the first one. We want them to finish first, second, and third. Very specific. It does matter. The person that finishes second gets the silver. They don't get the gold. So it's a different order each time. So in A, order matters. So we are either using our permutation formula or the fundamental counting principle. If you're using your permutation formula, we've got 5 people in this race, and we are ordering 3 of them, first, second, and third. So there are 60 different ways that these swimmers can finish first, second, and third. If you would have used the fundamental counting principle, 5 of them could have finished first. Once one of them finishes first, there are 4 left to finish in second spot. Once we've chosen another one, there are 3 people left that could finish in third. And that gives us 60. When you look at B, though, we are just qualifying for the top 3 finishers. It doesn't matter what order. So if Abby, Bree, and Callie finish in that particular order, first, second, and third, that group of 3, it wouldn't matter if it went Bree, Abby, Callie, or Callie, Abby, Bree. As long as those 3 are the top 3, we have one way. We have one combination. So here, order does not matter. So we are using combinations. So we've got 5, and we're choosing 3. So there are 10 different ways that this could occur. So hopefully you see the difference there. In the first one, we were specifically giving them a position, whereas in the second, we just wanted the group of the top 3. Didn't matter who was first, second, or third. So when solving counting problems, you need to determine if order plays a role in the situation. Once this is established, you can use the appropriate permutation or combination formula. So we've got a piano teacher and her students are having a group photograph taken. There are 3 boys and 5 girls. The photographer wants the boys to sit together and the girls to sit together for one of the poses. How many ways can the students and teachers sit in a row of 9 chairs for this pose? So there's a lot of information here. All right, and we want to figure out, does order matter or does order not matter? Order does matter in this case. It matters if you're sitting next to Sally in this picture or Jenna in that picture. All right, the order is important, but within the order, we're not just ordering 9 people. Within those 9, we also want the teacher, we want the boys together, and we want the girls together. So we've got 3 distinct blocks. We've got the teacher, we've got boys, and we've got girls. And in those blocks, they can be arranged in a variety of ways. But then those blocks themselves can also be arranged in a variety of ways. What we do know is that there's only one teacher. We know there are 3 boys, and we know we are ordering them, and we know we are putting all 3 of them together. So we can use a permutation formula. 3 boys, and we're picking 3 of them for this order. Or you can choose to just say 3 factorial. because remember, if you are using all of the items, or in this case, all of the boys, 3p3 is the same as 3 factorial. So whichever one makes more sense to you. For the girls, there are 5 girls, and we are ordering all 5 of them. So 5p5 or 5 factorial. It's up to you. So all of these have to be done, because now we're ordering the boys and we're ordering the girls, and we've got the teacher. But does it have to go teacher, then boys, then girls? No. There are 3 items, 3 blocks, that we can order in any of the 3 ways, or 3 factorial. So what we actually have in this calculation is 1 times 3 factorial times 5 factorial times 3 factorial. We have to multiply all of those together, and there are 4,320 different ways these 9 people can be organized for a photograph where the boys are together, the girls are together, and the teacher is outside of these groups. Let's look at this one. Combination problems are common in computer science. So this one's already telling you it's a combination problem. Gotta love that when they actually tell you up front. Suppose there is a set of 10 different data items represented by A, B, C, D, E, F, G, H, I, J to be placed into 4 different memory cells in a computer. Only 3 data items are to be placed in the first cell, 4 in the second, 2 in the third, and 1 in the last. How many ways can the 10 data items be placed in the 4 memory cells? Now, what we have to understand is that within each cell, it doesn't matter what order. So it doesn't matter if in the first cell where we are allowed to place 4, it doesn't matter if we go A, B, C, D or B, A, C, D. If those 4 are in there, it is a combination. All right? So we know that we have 3 data items in the first one, 4 in the second, 2 in the third, 1 in the fourth. So we have to find all of these possibilities. We're going to start with one of them. So if we're going to do cell 1, we have 10 items right now to choose from, and we are going to choose 3 of them. So we get 120 different ways that this is possible. So we've placed 3 into cell 1. Now we drop down to cell 2. We've already placed 3 though. There's only 7 items left to choose from. And in cell 2 we can put 4 of them. And we can do this 35 different ways. Now we've plunked them into cell 2, so it drops down to cell 3. We had 7, we put 4 up in cell 2, so we're only left with 3 items. We're going to choose 2 of them. There are 3 ways we can do that. Now, what's left to go into cell 4? There's only 1 item left. We only need 1 item. There's 1 way that we can do this. So now we have all of the combinations for each particular cell. So how do we find the total? We would multiply these together because these are an and. We have combinations for cell 1, and for cell 2, and for cell 3, and for cell 4. So we end up with 12,600 different ways that these data items can be put into the memory cells. How many different 5-card hands that contain at most 1 black card can be dealt to 1 person from a standard deck of playing cards? All right, we have to decide if order is important. Does it say when that black card needs to be dealt? Does it say it has to be first, second, last? The answer is no. It is just you are being dealt 5 cards, and at most there is 1 black card. So this one here is a combination because order is not important. Again though, at most, that's like the at least questions. We're going to have cases here. So we've got our first case. Well, we could have 1 black card, and that would mean we would have 4 red cards. Now it said at most 1 black card. So is our second case 2 black cards? No. It is that we have 0 black cards and all red cards. That's what at most means. So now we can go and we can find each set of combinations for each case. 1 black card. There are 26 black cards in a deck. We're going to choose 1 of them. And then we want the 4 reds, and it's an and, so we use multiplication. There are 26 red cards. We want to choose 4 of them. 388,700 different ways that this can be done. Let's look at our next case. We want to choose 0 blacks. So there's 26 blacks to choose from. We're choosing 0 of them. There are 26 red to choose from. We want 5 of them. We get 65,780. Now remember, in a case situation, it's case 1 or it's case 2. Or means add. So we add up those 2 sets of options, and we have 454,480 different ways that this could occur. All right, we're going to challenge you a little bit here. How many 3-letter arrangements can be made using the letters in the word books? Permutation or combination? Well, on the outside looking in, it looks like it's going to be a permutation because we're talking about arrangements. Arrangements usually refers to order. So we want to order these. But we've got a little bit of a situation here. We're only going to choose 3 letters. We've got some repetition. So we have to consider the options. There are some cases here. If we are going to choose 3 of these letters, is it possible to choose an arrangement that has no O's in it? And it is, because there are 3 letters that are not O's. So in our first possible case, we might find all of our permutations, so all of our arrangements, where we have no O's. What's some other cases we could have? Could we have an arrangement of 3 letters where there is only 1 O? And the answer would be yes. You would have 1 O and 2 of the other 3 letters. So we could have a possibility where we have just 1 O. Are there any other possibilities? Hopefully you're saying yes. Could we have a 3-letter arrangement that has 2 O's in it? Yes, we could. There could be 2 O's and 1 of the other letters. So now here are all of our possibilities. So what we now need to do is we need to find the combinations of each of those cases. We are specifically looking for arrangements. So we are going to end up having to use permutations. But before we can use permutations, we have to find the possible combinations of choosing letters that do not have O's, or choosing letters that have, or 3 letters that have only 1 of them being an O, or both of them being an O. So if we look at the first case, how many letters are not O's? Because in this first case, we aren't going to choose and order any O's. So we have 3 letters that are not O's. We are making 3-letter arrangements, so we need to choose all 3 of them. So that's how many different combinations of 3 letters we have that are not O's. But now we want to arrange those. So there are 3 letters to arrange. And we're going to arrange all 3 of them, so 3 factorial. When we find that out, we get 6. Now we want to look at the O's. We want to choose 3 letters, one of them of which is an O. So we are going to have 1 O that we're choosing. Now there are 3 non-O letters, but we only need 2 of them this time because we need 2 that are not O's and 1 that is an O. Once we have chosen 3 letters, we need to arrange those. So times 3 factorial. So there are 18 different arrangements that have only 1 O. And these are smaller quantities, so that if you can't visualize it right now, you could go through and write it out. You could take this word books and find all the possible 3-letter arrangements, and you would see that there are 18 of them that have just 1 O. Now we want to find all the possibilities where there are 2 O's. So what we have 2 O's, and we're going to choose both of them. We have 3 non-O's. We're only going to choose one of them. But here's something to remember. Repetition. We need to divide by the ones that repeat. And there are 2 O's that we are specifically using. So we need to divide out by 2 factorial. Now we're going to take all 3 of the letters we have chosen and we are going to arrange them. There are 9 different ways that this can be done. So when we add these all up, there are 33 different ways that we can take the letters from the word books and arrange them, so order is important, in 3-letter arrangements. And again, it's not a large number, so if you wanted to draw it out and visualize it so that you can see how 33 occurs, you could do that. So the biggest thing from today's lesson is you have to read the question and determine, is order important or is order not important? And once you have that figured out, it's just using either your permutation or your combination formulas.